Next speaker is Christian Meyers from the School of Engineering at Deakin University. He's also presenting work with Kaja Antlej. Their paper, 3D Printed Puzzles for STEM Outreach and Cultural Preservation, aims to engage the public of the Greater Geelong region with some of their own industrial heritage. So, Christian, over to you.
Yeah, thanks, guys. I'm Christian. I'm really pleased to be here today to present. Albeit digitally, my project, which is 3D printed puzzles for STEM outreach and cultural preservation. And it's a little bit of a shift in thinking from current data capture and visualization in terms of that end user interaction, in that it's using modern digitization techniques of 3D scanning and photogrammetry, and then computer-aided design to recreate tangible historical assets that could be placed back into the hands of users as object-based learning tools. But before I get into it, a little bit about me first for context. I come from a background in automotive, having spent a decade working as a technician with a specialisation in historic and collectible exotic vehicle restoration. And I since am now working in life sciences, but I returned to university studies as a mature age student and recently completed my undergraduate honours degree in mechanical engineering at Deakin University here in Victoria. It occurred to me during this time that I could leverage my past experiences in automotive to create what became a final year project that reflected my passion in recreating and salvaging significant automotive history for the enjoyment of future generations. Yet this time, instead of doing so through more traditional old-fashioned techniques, to explore the possibility of creating learning opportunities for young students through more modern design and advanced manufacturing methods, while simultaneously drawing that attention to significant historical achievements that kind of led us here in the first place. The concept actually originated as creating a toy car, something that could be broken down into its basic constituent parts and then reassembled in a puzzle format and potentially integrated into VR or AR. But ultimately the scope narrowed into the development of a 3D printed puzzle of this 1934 Ford Coupe utility aimed at providing STEM outreach opportunities for early primary school students in the Greater Geelong region here in Victoria, Australia. The model itself is designed to be a historically accurate and scale representation of this ute, and it's positioned to offer a tactile object-based learning opportunity that heralds a design of immense cultural significance for that Greater Geelong region. As a bit of background, Geelong is the second largest Victorian city outside of the state's capital here in Melbourne, and from its inception in the early 1900s, it really established itself as one of the leading manufacturing centres in Australia, and spearheaded by what is now the defunct Ford Motor Company manufacturing facility, where in 1934, a young 22-year-old designer named Lou Bant designed this first ute. And it's actually a really important thing to consider, the significance of this achievement. That ute went on to become a staple of Australian culture and a global icon, yet the history and the manufacturing identity of its birthplace, as has been seen with many former industrial hubs around the world, is now becoming overshadowed by a more modern push for innovation. And in Geelong's case, this is primarily within service industries and education. It was determined through extensive local research and community surveys conducted both by myself and fellow Deakin University researchers as part of the Geelong Inventions Past and Future Symposium earlier this year, that 95% of the participants viewed this concept of integrating manufacturing traditions and cultural heritage into the curriculum of young people in the region as one of great value for the future of the community, by helping to highlight the significance of those past innovations and to encourage younger generations to get involved in using the history to progress the innovative goals for the future. Further to this, the creation of something tangible and something hands-on that could be demonstrated within local museums or even manufactured and built within a classroom environment could prove beneficial in engaging those students in STEM through the use of this object-based learning resource. But More importantly, to increase that exposure and awareness to the cultural significance of the local design and engineering by showcasing what was the most iconic of those local inventions in a way that's never really been available before. So prior to my involvement, the Geelong Inventions team, with particular mention to Matthew George and Munsa Ogrizek. Munsa is actually presenting her work in 3D VR interaction tomorrow, so be sure to check that out. But they'd conducted significant prior work in digitising this ute through their own virtual and augmented reality museum and gamified experiences. This included the 3D scanning and photo telemetry of a privately owned vehicle due to there actually being no access to a quality example in the public domain within the region. This prior work was highly valuable in providing that base point cloud geometry required to then further explore the reverse engineering workflow process necessary to allow this geometry to be manipulated within CAD software. But why reverse engineer for CAD in the first place? It's actually commonplace nowadays to simply output that point cloud data from the 3D scanner directly to an STL file type that can be ready for 3D printing in its native form, with a model able to be scaled within slicer software if needs be. It is in fact actually becoming more and more common even to find 3D scanning to 3D printing being used within museum environments for artifact preservation and restoration, with the British Museum even cashing in on this convenience of the technology by monetising their 3D printed replicas and making them available to the public in the gift shop. And this type of utility really adds another element to the project, which I'll touch upon a bit later, but it helps to highlight the importance of a reliable and a simple reverse engineering process that could be placed into the hands of layman users and educators to really take advantage of the technological potential. So to gain an insight into why, I guess, this reverse engineering process is necessary in this instance, it's important to identify the fundamentals. That 3D scanner maps the object or surfaces being scanned as a set of data points in space. And these data points are then joined together with vertices, commonly converted into polygon, triangulated, or spline-based surface mesh. And the geometry is not editable in this native format. The fidelity of that rendered output is typically dictated by the granularity in which these mesh sections are assigned and or interpolated between each other. And this is performed as a post-processing rendering task within graphics programs. Increasing this fidelity naturally allows for greater accuracy inherent to the original scanned object. In this case, the fidelity of that 3D scanned output had been simplified as acceptable for gamification and VR use. However, when performing a test 3D print, that surface quality and the detailed aesthetic is actually quite poor and not really suitable as an interactive representation of that original object. To enable editing of the geometry, then, it must be imported into CAD and essentially used as a template to then recreate from scratch solid and editable bodies. As I'm using the Autodesk Inventor, Autodesk suite of products in this case, that FBX file type provided to me was then converted in 3ds Max to a step file and imported into Inventor as a single surface body entity. The translucency of the surface body was then suppressed to aid in that visualization, and the remodeling process could really commence from there. It's worth noting that even in this simplified form, that surface body consists of over 52,000 triangulated facets, despite that very low fidelity quality, particularly when considering the organic and non-geometric surfaces. And this puts a really heavy processing load on CAD software, particularly in those initial conversion steps. So I guess better defining this 3D scan to CAD framework was really one of the most critical aspects of the project, with the goal to develop a methodology that could be transferable between both complex and basic freeware CAD packages, using common CAD tooling, and then digital skills that could be readily taught on a fundamental level. The methodology I followed is not really limited in bringing the physical object into that editable virtual space. but is also more importantly bringing that object back into the physical world with that critical end user consideration. So that design process was really driven by an iterative, staged approach to product development, with each stage reflecting IDEO's three lenses of innovation framework, verifying desirability, viability, and feasibility, and then building upon the learnings from each of these previous stages through design for X principles. These principles are defined as the design for manufacturing, assembly, reliability, and most critically, safety. From here, that remodeling process could really get underway. From extensive literature review that was in line with this methodology, initial product specifications such as the scale, the complexity, the size of the individual pieces, any functionality, and particularly the historical aesthetic of that puzzle were determined. And then it was ultimately divided up into 15 components using the boundaries of the surface body facets as the mating surface divisions between each of those puzzle pieces. For the bulk of the more geometric bodies, such as this rear section, this involved tracing an outline of the shape from the surface geometry nodes, projecting it then onto the neutral plane, and using traditional subtractive modeling techniques based on the dimensions of the 3D scanned surface geometry to yield new solid bodies that are native in CAD. For the more complex and organic surfaces, this was performed by tracing those control points as specified in the scan surface geometry, and then creating an interpolated splined or Bezier surface approximation across that control grid, similar to that was seen in traditional timber buck metal forming in industry. This could then be lofted into a solid body and mated to the corresponding geometric face, and then combined as a single body with that existing part. The process was followed for each of the components through multiple iterations, and following those design for X principles, allowances were made for magnetic interfacing, operable components, and once it was all finalized, it was then scaled down in bulk to 1 to 15 scale. Now, I won't go too much into the detail about that testing process. I don't want you all to fall asleep, but it's worth mentioning that the design for safety aspect is actually what ended up proving that most challenging. Australian New Zealand Safety of Toy Standards dictate, of course, the testing protocols required for their approval. So identifying potential weak points through a design failure analysis and then transferring from that matrix into FEA where possible really proved crucial in saving time and speeding up that iterative design process prior to then any physical or destructive testing of the 3D printed parts. Interestingly, performing the FEA on solid homogeneous parts ended up yielding conservative results when comparing to applying these same loads to 3D printed objects. And it becomes evident really quickly that the behavior of 3D printed parts are very different to those manufactured using traditional methods. For museum objects that are going to be on static display only, it's kind of a moot point, but it is really a crucial consideration when designing end-use 3D printed parts that are to be interacted with physically or directly by the user, particularly in the case for objects where vulnerable features such as the roof section of this model are present. There are literally hundreds of design and manufacturing variables that can alter the mechanical behavior of 3D printed objects, and the key challenge here was finding the ideal combination of these to really maximize those desired mechanical properties of sort of strength, flexural modulus, and toughness, for example, while attempting to maintain a high level of surface quality to reflect the key historical aesthetics of that design. It's also important to understand that the properties of one component may actually vary significantly from another, despite the use of the same material and the same manufacturing method. And it really highlights the importance of these engineering considerations when using this type of medium for end-use parts. In total, this CAD redesign was actually heavily time-consuming, due primarily to the trial and error nature of the process for me. I should also mention I've had a few years of basic CAD experience in this software before taking on the project, so I can't be considered an entry-level user. And this really highlights how steep of a learning curve it can be to this type of reverse engineering for those without a defined framework to follow. Encouragingly, in testing this framework on 2 separate entry-level users with no formal engineering or CAD experience, they were able to recreate some of the more challenging components of the model in roughly about a quarter of the time that it took me to actually develop it in the first place. While this is very subjective, it offers a really great early insight into the potential for a savvy educator within a classroom or a museum environment to pass on this type of skill to younger users who nowadays, thanks to multiple open source online data repositories, can access and modify and create their own interactive scale models of historical objects and industrial heritage from 3D scan data. Ultimately, this approach allowed for a very targeted final design that was 3D printed in the home environment, thanks to COVID, in environmentally sustainable and user-friendly PLA, polylactic acid, using a fused deposition modeling technique. At 500 grams and 1:15 scale, this puzzle consists of 15 individual magnetically interfacing pieces designed for the ease of handling and safety for the target market, and is an aesthetically representative, interactive reproduction of that original 3D scan, and fundamentally validated as safe for use within the target age group. Furthermore, the workflow from that scanner to CAD is quite well defined and easily repeatable within a typical classroom environment, using virtually any basic CAD package with access to an FDM printer and some off-the-shelf componentry. In addition, a secondary prototype was printed using Deakin University's powder bed printer to demonstrate the potential of coloured and textured 3D printing in terms of high fidelity artifact preservation. And this showcases where hopefully the technology is heading in the years to come for basic users. It's currently cost prohibitive for hobbyists and small institutes, but it is not beyond the reach of larger educational institutes and museums, for example. Unfortunately, this material does not offer those mechanical properties of other more popular methods, so it's not necessarily useful for the object-based learning outcomes, but it does produce an output that is in line with a lot of the user feedback, the desired colour and realistic texture. And it's an excellent choice for static artifact preservation and one-step historical object reproduction due to this. Now, what I find most captivating, I guess, about any form of 3D printing is that while each method does have these limitations offer a really fantastic and unique opportunity for users to think beyond the form and to watch something complex be created essentially from nothing in front of their eyes in real time with the inherent fingerprints of their own design decisions. The perfect example of this is often considered an unsightly hallmark of 3D printing, but those visible surface build lines can actually offer a terrific discussion point. And many users have expressed intrigue and have attracted that, fantastic educational and outreach opportunity in terms of encouraging critical thinking and a deeper understanding of design and engineering considerations in product realization. Further to this, the concept opens up potential for a range of mixed reality experiences outside of traditional cultural heritage education or even standalone VR or AR, with hands-on artifacts able to become integrated into that virtual space to recreate experiences such as being on the floor of a long-forgotten vehicle assembly line, to piecing together a skeleton or changing the color scheme of a prehistoric creature, to saying that creative play with important cultural objects from a region's past. Partnering with educational and heritage institutes and working towards creating these mixed reality environments is a really large part of the future scope for this project. Further research also into how this framework may be able to be applied or adapted outside of industrial heritage to more complex and large-scale cultural artifacts, architectural heritage, or freeform sculpture, with the aim to bring these associated object-based learning and STEM opportunities into more classrooms and indeed even into the home environment in a creative and a customizable way. And yeah, with that, I'd like to again just pass on my thanks for the opportunity, and I'd be happy to take any questions or comments. So cheers.